Hello everyone, welcome back to the channel. Today, we're diving into a foundational topic in cybersecurity that often confuses people: hashing versus encryption. These two concepts are critical, but they're not interchangeable. Hashing and encryption play distinct roles in securing data, and understanding their differences is essential for anyone working in cybersecurity or preparing for the CompTIA Security Plus exam. In this video, we'll cover the definition and purpose of hashing and encryption, the mechanics of how each works, key differences between them, real-world applications, and common challenges and best practices. By the end of this video, you'll not only understand these concepts, but also be ready to apply them in real-world scenarios. Let's get started. Section 1. What is hashing? Let's start with hashing, a process you've likely encountered, whether you realized it or not. Definition of hashing. Hashing is the process of transforming input data, like a password or file, into a fixed-length string of characters, known as a hash value or digest. This process ensures data integrity by creating a unique fingerprint of the original input. Think of hashing as a digital fingerprint. No matter how big or small the original data is, the fingerprint is always the same size. Key characteristics of hashing one-way functionality. Hashing is designed to be irreversible. Once data is hashed, you cannot reconstruct the original input from the hash value. Imagine turning a cake back into its raw ingredients. It's just not possible, and that's the beauty of hashing in security. Fixed length output. Regardless of the input size, the hash value is always the same length. Example: a one-page document and a 1,000-page book will both produce hash values of the same length. This consistency is what makes hashing so effective for data comparison and verification. Deterministic nature. The same input will always produce the same hash value. This ensures reliability in verifying data integrity. If you hash the word cybersecurity today, tomorrow, or years from now, the hash will always match. Common hashing algorithms. SHA, Secure Hash Algorithm. SHA-256 is one of the most popular algorithms, offering strong security and wide adoption. Example: SHA-256 is used in blockchain technology to ensure data integrity. MD5, Message Digest 5. Once widely used, MD5 is now considered insecure due to vulnerabilities, but still has niche applications in non-critical systems. HMAC, Hash-Based Message Authentication Code, combines hashing with a secret key for added security, often used in API authentication and secure communications. Each algorithm has its strengths and weaknesses, so choosing the right one depends on the application. Applications of hashing password storage. When you create a password, it's hashed and stored in a database. When you log in, the system hashes the entered password and compares it to the stored hash. This ensures that even if the database is breached, attackers only get the hashed values, not the actual passwords. File integrity verification. Hashing is used to verify that files haven't been tampered with during transfer or storage. Example: software vendors provide hash values for downloads to ensure the file hasn't been altered. Digital signatures. Hashing ensures the integrity of a signed document, verifying that it hasn't been modified after signing. Section 2. What is encryption? Now let's shift our focus to encryption, a process designed to keep data confidential. Definition of encryption. Encryption transforms readable data, known as plain text, into an unreadable format called ciphertext. Unlike hashing, encryption is reversible and requires a key for both encryption and decryption. Encryption is like locking your data in a safe. Only someone with the correct key can unlock it. Key characteristics of encryption. Reversible process. Encryption is designed to be decrypted back into the original plain text using a key. This reversibility is what makes encryption critical for secure communications. Key-based security. Encryption relies on keys, which can be symmetric, one key for both encryption and decryption, or asymmetric, a pair of public and private keys. Ensures confidentiality. Encryption ensures that data remains private and accessible only to authorized parties. Common encryption algorithms, AES, Advanced Encryption Standard. AES is highly secure and efficient, making it ideal for encrypting sensitive data at rest and in transit. Example, used in securing VPNs and Wi-Fi networks. RSA, Rives Shamir Adleman, a widely used asymmetric encryption algorithm often employed for secure key exchanges. ECC, elliptic curve cryptography. Lightweight and secure, ECC is frequently used in mobile devices and IoT applications. Applications of encryption secure communications, encrypting emails, messages, and voice calls to ensure privacy. Example, WhatsApp uses end-to-end encryption to protect messages. Data encryption at rest, protecting data stored on hard drives, databases, and cloud storage. Authentication and digital certificates, verifying identities in secure communications through encrypted certificates. Section 3. Hashing versus encryption. Now, let's compare hashing and encryption side by side to highlight their differences. Purpose hashing ensures data integrity by creating a unique fingerprint of the data. Encryption ensures confidentiality by converting data into an unreadable format. Reversibility. Hashing, irreversible. You cannot reconstruct the original data from the hash. Encryption, reversible. Ciphertext can be decrypted back into plaintext. Key usage. Hashing, no keys are used, it's purely mathematical. Encryption. Keys are essential for both encryption and decryption. Think of hashing as creating a fingerprint, while encryption is like locking the data in a vault. Section 4. Real-world applications. Hashing and encryption are often used together in modern systems. Password security. Passwords are hashed before storage, but encryption might protect the hash during transmission. Digital certificates. Encryption protects the confidentiality of certificates, while hashing ensures their integrity. Secure communications. Messages are encrypted, and their integrity is verified through hashing. Combining these methods ensures both data integrity and confidentiality. Section 5. Challenges and best practices. Let's touch on some challenges and best practices for both hashing and encryption. Challenges. Hash collisions occur when two different inputs produce the same hash value. Stronger algorithms like SHA-256 reduce this risk. Key management in encryption. Securely storing and managing keys is critical. Losing a key can make encrypted data unrecoverable. Best practices use strong algorithms like AES for encryption and SHA-256 for hashing. Regularly update and rotate encryption keys to reduce risk. Combine hashing and encryption for layered security in sensitive applications. Addressing these challenges ensures your systems remain secure and resilient. Conclusion. Presenter. To wrap up, hashing is best for verifying data integrity, while encryption ensures data confidentiality. Both techniques are essential in modern cybersecurity. Understanding when to use hashing, encryption, or both is crucial for designing secure systems. Whether you're studying for the CompTIA Security Plus exam or working on real-world security solutions, mastering these concepts is a must. Don't forget to like, subscribe, and share this video. Questions? Drop them in the comments. I'd love to hear from you.